Greetings and welcome to a new video about analog filter design. In this example we'll discuss the low-pass filter using a buffered circuit configuration. Of course we will see everything step by step in our calculations and verify these in SPICE simulations. Now before we jump to our design example, let's first discuss this buffered low-pass filter circuit. You see here the low-pass filter configuration using two buffers using an operational amplifier. This R1 and C1 is the first stage, and it is actually buffered by this operational amplifier circuit, and we have also this R2 and C2, again a low-pass filter buffered by this operational amplifier. So you see here two buffers and two stages, so which will be a second order low-pass filter circuit. The transfer function of this circuit, which is then the VO over VI, which is output divided by the input voltage, is given by this expression. You see here the product of all the components in our circuit in the numerator, divided by a second order expression, which is then S squared plus 1 over R1 C1 times S plus, and again 1 over the product of all the components in this circuit. Now in this case we can use the equal capacitor method, so we can select the capacitors equal to each other, so C1 is equal to C2, and define it as C, and it will reduce also the number of unknowns and also speed up the design process. Now then we have, if you do this, that will be then 1 over R1 times R2 times C squared. That's the numerator, and you get here 1 over R1C, and this term will be then 1 over the R1 times R2, again C squared, as we have it in the numerator. Now the standard form of a second order low pass filter is given by this expression. You see here three parameters, the K, omega n, and also our quality factor Q. The K is also called the passband gain or the DC gain. The quality factor Q will determine the shape, the sharpness of our filters. And omega n, the natural frequency, is related to the resonance frequency we will see shortly. If you now compare the terms using this transfer function and the standard form of the transfer function, you see direct that the omega n squared must be this, which is shown here. The K is always 1 because the K times the omega n squared must be this, but this is of course in the standard form again omega n squared, so the K must be 1, so you will have always a unity gain in this filter circuit. The 1 over the R1 and the C1 will be then omega n over Q, which is then actually shown here. So we have here actually three equations, but actually this is always 1, so you have two equations where you need to calculate for component values. That means we need to select some values. We will see that shortly in our design example. Now the design equations, which are of course the important parts. Now the omega n can be calculated by taking the square root of the left and right hand side, which is shown here. If we use C1 is equal to C2, so the equal capacitor method, then our expression will be like so. The Q can be calculated by rewriting this expression, so Q times 1 is equal to omega n times R1 C1, which is shown here. We know what the omega n is, which is actually shown here in general form. Now we have this expression. Now you can see here that we have an R1 and C1 in the numerator, but you also see that here in the denominator, but in the square root. That means this part will be then the square root of that product, and you will lose the R1 and the C1 here, and in fact you get actually this expression. If you now have the C1 is equal to C2 condition again, so you will use that, these two values will cancel each other out, and you will have an expression where you see the square root of the R1 over R2. This is of course a very simple expression, because if you want, for example, a Q, let's say 5, then you can say I will take the ratio here of 25. That means you will then have the square root of 25 will be then Q of 5. The cutoff frequency, very important parameter, we will see that shortly in our design example, is related to that omega n, natural frequency, and the cutoff frequency. And the resonance frequency we will calculate also shortly in our design example is again related to that quality factor and the natural frequency. There is a gain peaking, which is called the MR, is happening at that resonance frequency, which is then given by this expression. So again, the parameters omega c, which is our cutoff frequency in radians per second, omega r, resonance frequency, radians per second, and MR is our gain peaking at that resonance frequency. So these are very important parameters and equations we need to use. And this is only valid for the Q, which is larger or equal to 1 over the square root of 2. So we cannot use it for, let's say, Q is equal to 0.4. Okay. Let's go in more detail and see the effect of the quality factor. This is a general Bode plot of a second order peaking low pass filter. You see here the low frequency gain and also the maximum gain here, and this distance is what we call the MR, which is our gain peaking. Of course, this can be also starting at some other value, let's say 5 dB, and then you go up. This distance is actually where we talk about, but for this circuit we always start at 0 dB specifically. And if you want to convert that to dBs, you always do 20 log of that value. This is always give you a scalar value. And this is happening, this gain peaking, at that resonant frequency omega using this formula. And here you see the cutoff frequency, which is defined as 3 dB lower than the baseline here, so it is at -3 in this case. And here you see some values for the quality factor, because this is only again valid for 1 over the square root of 2 or larger for the quality factor. So if you take exactly this value, you will get an MR of 1, which is also 0 dB if you use this formula. Now if you go to a quality factor as 1 or 1.52, so if you increase that, you will also increase your gain peaking. That means this will go and now it will be larger and larger and larger, where you have a larger Q. Okay, now in more detail and some examples of the quality factor. See here the quality factor 0.7071, again our edge for our condition. Q is 1.5, so we increase and then Q. So you see actually that indeed the shape is getting sharper. That is actually that the selectivity factor will be then also sharper, but you get of course more peaking. That is the cost actually for this situation. And we can now look at in more detail what the actual gain peaking is for the Q is 2, Q is 1.5, and also for Q is 1. And again, there is no peaking for Q is 1 over the square root of 2. Okay. Let's now go to our design objective and our example here. We will have a buffered active low pass filter circuit. That's shown here again, we just discussed. We have specifications. The cutoff frequency must be 2 kHz. The passband gain should be 1 or 0 dB, and we will have a gain peaking of 8 dB. And then we will calculate also the resonant frequency of our final design. Okay. First, the calculations. Our gain peaking is given as 8 dB. Let's first use that value and first convert that to a scalar, which is then 10 to the power 8 over 20, which is here approximately 2.51. Now we know the formula for the MR in the scalar form, that is this formula. Now when you substitute here this 2.5119 and you solve this using a solver, that will give you a Q of 2.4594. Now the quality factor we know. We can now use the quality factor formula in order to calculate the other components, R1, R2, C1 and C2. But this is the formula we get. We see here the Q is equal to the square root of the R1 times C1 over R2 times C2. So we have here 4 unknowns. You can of course set the equation. So you can say the left side is 2.4594. Again, we see here 4 unknowns. So we have too much unknowns here. So what can we do? Now we leave it for the moment. And we will see what we can do if we use also other specifications here. The cutoff frequency formula, we know that is the omega n times the square root of this term. Again, you see the quality factors, we just calculated. We know the cutoff frequency, which should be 2 kHz, but this is of course in radians, so we need to do 2 pi times 2000, which is shown here. And everything is here substituted also for the quality factors. So we can now actually say this is just a number, and then this is then 4000 pi over this number, and that will be the omega n, which is then in this case 8333 radians per second. Now we go to the formula for the natural frequency, which was also given, which is 1 over the square root of the product of the 4 components here. And now we can write it like so. We say 8333 is equal to 1 over the square root of the products. And that is again 4 unknowns. So how can we now continue? Let's now first designate this equation number 1, this part, and equation number 2 for this part. Okay. If we now select the capacitors equal to each other, so that is the equal capacitor method. So I will make C1 is equal to C2, which is then 10 nanofarads. And then we will have, for this equation, which will be then the square root of R1 over R2, because I will then lose C1 and C2, because those are equal to each other. And I also get here 1 over the square root of R1 times R2 in the square root, of course, and then times C outside, which is actually shown here. And since we know what C is, which is then 10 to the power minus 8, which is then 10 nanofarads, which is actually also shown here. So we see here now two equations and two unknowns, and these two unknowns are R1 and R2. Okay, we can rewrite this expression so we can square the left and right hand side. So you see here the R1 over R2 is the square of that Q. And then you can say R1 is equal to this value times R2. And this value squared is in this way 6.0488 R2. Now we can use this formula or expression for R1 in terms of R2 in this expression for the omega n. So we will do that. So this is an 8333 is equal to 1 over the square root of, this is R1, this part, and this is R2 again. So we have now actually one unknown, which is just R2, and times again this 10 to the power minus 8. Now we can now take out this R2 out of this square root because that is just R2 squared. So that's actually this. And when you now calculate this further and express the value for R2, that will be then like so, because you can swap these places, and that will result in 4.879 kilo. So we know R2. Now, since we know R2, we can also calculate R1 using this formula that's shown here, and that will be then actually this 29.51 kilo. So we have selected our capacitors, and we have now calculated using that the resistor R1 and R2. Now the final one is our resonance frequency. That was also the question in place here. So that is then given by this expression. We know the resonance, the natural frequency and the quality factor. So that will be also given like so. That will be then 7,981 radians per second. Okay, let's now go to the simulation results, the Bode plot. You see here the gain in blue, the plot. This is the gain in the vertical axis in dBs, and this is our log scale frequency. And this is the circuit we have now built in the SPICE simulations. You see here the input, the output, two operational amplifiers, and the resistors and the capacitors we have calculated. You see first here the DC gain, which is 0 dB, so which is indeed what we want, because we want to have a passband gain or 0 or the DC gain of 1. The cutoff frequency, which is then going down from this baseline by 3.01 dB, happens at indeed 2 kHz, which is also what we want, so this is also correct. And the gain here is 8 dB, so going up to 8 dB, which happens at 1.272 kHz, which is the resonance frequency. Now we have calculated our resonance frequency, which was in radians per second, 981 radians per second, converted that to the hertz, which will give you 1270 hertz, which is then 1.27 kilohertz, which is off by 2 hertz here, which is really due to the rounding off errors. So this is actually as we have it also in the simulations. So we can say we have verified our calculations and also met the design specifications for this example. Alright, it was our example considering the active low-pass filter using a buffered configuration as shown here. This is a second order low-pass filter design. We have first looked at the transfer function and derived from there the design equations and verified these in SPICE simulations. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.